the first part of Chapter 1 of The Outline of Science. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. This recording is by Mark Smith of Simpsonville, South Carolina. The Outline of Science, edited by J. Arthur Thomson. Chapter 1, The Romance of the Heavens. First part, The Scale of the Universe, the Solar System. The story of the triumphs of modern science naturally opens with astronomy. The picture of the universe which the astronomer offers to us is imperfect. The lines he traces are often faint and uncertain. There are many problems which have been solved. There are just as many about which there is doubt, and notwithstanding our great increase in knowledge, there remain just as many which are entirely unsolved. The problem of the structure and duration of the universe, said the great astronomer Simon Newcomb, is the most far-reaching with which the mind has to deal. Its solution may be regarded as the ultimate object of stellar astronomy, the possibility of reaching, which has occupied the minds of thinkers since the beginning of civilization. Before our time, the problem could be considered only from the imaginative or the speculative point of view. Although we can today attack it to a limited extent by scientific methods, it must be admitted that we have scarcely taken more than the first step towards the actual solution. What is the duration of the universe in time? Is it fitted to last forever in its present form, or does it contain within itself the seeds of dissolution? Must it, in the course of time, in we know not how many millions of ages, be transformed into something very different from what it now is? This question is intimately associated with the question whether the stars form a system. If they do, we may suppose that system to be permanent in its general features. If not, we must look further for our conclusions. The heavenly bodies. The heavenly bodies fall into two very distinct classes so far as their relation to our earth is concerned. The one class, a very small one, comprises a sort of colony of which the earth is a member. These bodies are called planets, or wanderers. There are 8 of them, including the earth, and they all circle round the sun. Their names, in the order of their distance from the sun, are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and of these Mercury, the nearest to the sun, is rarely seen by the naked eye. Uranus is practically invisible, and Neptune quite so. These 8 planets, together with the sun, constitute, as we have said, a sort of little colony. This colony is called the solar system. The second class of heavenly bodies are those which lie outside the solar system. Every one of those glittering points we see on a starlit night is at an immensely greater distance from us than is any member of the solar system. Yet the members of this little colony of ours, judged by terrestrial standards, are at enormous distances from one another. If a shell were shot in a straight line from one side of Neptune's orbit to the other, it would take 500 years to complete its journey. Yet this distance, the greatest in the solar system as now known, excepting the far swing of some of the comets, is insignificant compared to the distances of the stars. One of the nearest stars to the earth that we know of is Alpha Centauri, estimated to be some 25 million millions of miles away. Sirius, the brightest star in the firmament, is double this distance from the earth. We must imagine the colony of planets to which we belong as a compact little family swimming in an immense void. At distances which would take our shell not hundreds, but millions of years to traverse, we reach the stars, or rather, a star, for the distances between stars are as great as the distances between the nearest of them and our sun. The earth, the planet on which we live, is a mighty globe bounded by a crust of rock many miles in thickness. The great volumes of water which we call our oceans lie in the deeper hollows of the crust. Above the surface an ocean of invisible gas, the atmosphere, rises to a height of about 300 miles, getting thinner and thinner as it ascends. Except when the winds rise to a high speed, we seem to live in a very tranquil world. At night, when the glare of the sun passes out of our atmosphere, the stars and planets seem to move across the heavens with a stately and solemn slowness. It was one of the first discoveries of modern astronomy that this movement is only apparent. The apparent creeping of the stars across the heavens at night is accounted for by the fact that the earth turns upon its axis once in every 24 hours. When we remember the size of the earth, we see that this implies a prodigious speed. In addition to this, the earth revolves around the sun at a speed of more than 1,000 miles a minute. Its path around the sun, year in, year out, measures about 580 million miles. The earth is held closely to this path by the gravitational pull of the sun, which has a mass 333,432 times that of the earth. If at any moment the sun ceased to exert this pull, the earth would instantly fly off into space straight in the direction in which it was moving at the time, that is to say, at a tangent. This tendency to fly off at a tangent is continuous. It is the balance between it and the sun's pull which keeps the earth to her almost circular orbit. In the same way, the 7 other planets are held to their orbits. Circling round the earth, in the same way as the earth circles round the sun, is our moon. Sometimes the moon passes directly between us and the sun and cuts off the light from us. We then have a total or partial eclipse of the sun. At other times the earth passes directly between the sun and the moon and causes an eclipse of the moon. The great ball of the earth naturally trails a mighty shadow across space, and the moon is eclipsed when it passes into this. The other 7 planets, 5 of which have moons of their own, circle round the sun as the earth does. The sun's mass is immensely larger than that of all the planets put together, and all of them would be drawn into it and perish if they did not travel rapidly round it in gigantic orbits. So the 8 planets, spinning round on their axes, followed their fixed paths round the sun. The planets are secondary bodies, but they are most important, because they are the only globes in which there can be life as we know life. If we could be transported in some magical way to an immense distance in space above the sun, we should see our solar system as it is drawn in the accompanying diagram, except that the planets would be mere specks faintly visible in the light which they receive from the sun. This diagram is drawn approximately to scale. If we move still farther away, trillions of miles away, the planets would fade entirely out of view, and the sun would shrink into a point of fire, a star. And here you begin to realize the nature of the universe. The sun is a star. The stars are suns. Our sun looks big simply because of its comparative nearness to us. The universe is a stupendous collection of millions of stars or suns, many of which may have planetary families like ours. The scale of the universe. How many stars are there? A glance at a photograph of star clouds will tell at once that it is quite impossible to count them. The fine photograph reproduced in Figure 2 represents a very small patch of that pale white belt, the Milky Way, which spans the sky at night. It is true that this is a particularly rich area of the Milky Way, but the entire belt of light has been resolved in this way into masses or clouds of stars. Astronomers have counted the stars in typical districts here and there, and from these partial counts we get some idea of the total number of stars. There are estimated to be between 2 and 3,000 million stars. Yet these stars are separated by inconceivable distances from each other, and it is one of the greatest triumphs of modern astronomy to have mastered, so far, the scale of the universe. For several centuries, astronomers have known the relative distances from each other of the sun and the planets. If they could discover the actual distance of any one planet from any other, they could at once tell all the distances within the solar system. The sun is, on the latest measurements, at an average distance of 92,830,000 miles from the earth, for as the orbit of the earth is not a true circle, This distance varies. This means that in 6 months from now, the Earth will be right at the opposite side of its path round the Sun, or 185 million miles away from where it is now. Viewed or photographed from two positions so wide apart, the nearest stars show a tiny shift against the background of the most distant stars, and that is enough for the mathematician. He can calculate the distance of any star near enough to show this shift. We have found that the nearest star to Earth, a recently discovered star, is 25 trillion miles away. Only 30 stars are known to be within 100 trillion miles of us. This way of measuring does not, however, take us very far away in the heavens. There are only a few hundred stars within 500 trillion miles of the Earth, and at that distance the shift of a star against the background, parallax the astronomer calls it, is so minute that figures are very uncertain. At this point the astronomer takes up a new method. He learns the different types of stars, and then he is able to deduce more or less accurately the distance of a star of a known type from its faintness. He, of course, has instruments for gauging their light. As a result of 20 years' work in this field, it is now known that the more distant stars of the Milky Way are at least 100,000 trillion miles away from the Sun. Our Sun is in a more or less central region of the universe, or a few 100 trillion miles from the actual center. The remainder of the stars, which are all outside our solar system, are spread out, apparently, in an enormous disk-like collection, so vast that even a ray of light, which travels at the rate of 186,000 miles a second, would take 50,000 years to travel from one end of it to the other. This, then, is what we call our universe. Are there other universes? Why do we say our universe? Why not the universe? It is now believed by many of our most distinguished astronomers that our colossal family of stars is only one of many universes. By a universe, an astronomer means any collection of stars which are close enough to control each other's movements by gravitation. And it is clear that there might be many universes, in this sense, separated from each other by profound abysses of space. Probably there are. For a long time we have been familiar with certain strange objects in the heavens which are called spiral nebulae. We shall see at a later stage what a nebula is, and we shall see that some astronomers regard these spiral nebulae as worlds in the making. But some of the most eminent astronomers believe that they are separate universes, island universes they call them, or great collections of millions of stars like our universe. There are certain peculiarities in the structure of the Milky Way which lead these astronomers to think that our universe may be a spiral nebula, and that the other spiral nebulae are other universes. Vast as is the solar system, then, it is excessively minute in comparison with the stellar system, the universe of the stars, which is on a scale far transcending anything the human mind can apprehend. The solar system, the Sun. But now let us turn to the solar system and consider the members of our own little colony. Within the solar system there are a large number of problems that interest us. What is the size, mass, and distance of each of the planets? What satellites, like our moon, do they possess? What are their temperatures? And those other sporadic members of our system, comets and meteors, what are they? What are their movements? How do they originate? And the Sun itself, what is its composition? What is the source of its heat? How did it originate? Is it running down? These last questions introduce us to a branch of astronomy which is concerned with the physical constitution of the stars, a study which, not so very many years ago, may well have appeared inconceivable. But the spectroscope enables us to answer even these questions, and the answer opens up questions of yet greater interest. We find that the stars can be arranged in an order of development, that there are stars at all stages of their life history. The main lines of the evolution of the stellar universe can be worked out. In the Sun and stars we have furnaces with temperatures enormously high, It is in such conditions that substances are resolved into their simplest forms, and it is thus we are enabled to obtain a knowledge of the most primitive forms of matter. It is in this direction that the spectroscope, which we shall refer to immediately, has helped us so much. It is to this wonderful instrument that we owe our knowledge of the composition of the sun and stars, as we shall see. That the spectroscope will detect the millionth of a milligram of matter, and on that account has discovered new elements, commands our admiration. But when we find in addition that it will detect the nature of forms of matter trillions of miles away, and, moreover, that it will measure the velocities with which these forms of matter are moving with an absurdly small % of possible error, we can easily acquiesce in the statement that it is the greatest instrument ever devised by the brain and hand of man. Such are some of the questions with which modern astronomy deals. To answer them requires the employment of instruments of almost incredible refinement and exactitude, and also the full resources of mathematical genius. Whether astronomy be judged from the point of view of the phenomena studied, the vast masses, the immense distances, the eons of time, or whether it be judged as a monument of human ingenuity, patience, and the rarest type of genius, it is certainly one of the grandest, as it is also one of the oldest of the sciences. The Solar System. In the Solar System we include all those bodies dependent on the Sun which circulate round it at various distances, deriving their light and heat from the Sun, the planets and their moons, certain comets, and a multitude of meteors. In other words, all bodies whose movements in space are determined by the gravitational pull of the Sun. The Sun. Thanks to our wonderful modern instruments and the ingenious methods used by astronomers, we have today a remarkable knowledge of the Sun. Look at the figure of the Sun in the frontispiece. The picture represents an eclipse of the Sun. The dark body of the Moon has screened the Sun's shining disk and taken the glare out of our eyes. We see a silvery halo surrounding the great orb on every side. It is the Sun's atmosphere, or crown, corona, stretching for millions of miles into space in the form of a soft, silvery-looking light. Probably much of its light is sunlight, reflected from particles of dust, although the spectroscope shows an element in the corona that has not so far been detected anywhere else in the universe, and which in consequence has been named coronium. We next notice in the illustration that at the base of the halo there are red flames peeping out from the edges of the hidden disk. When one remembers that the Sun is 866,000 miles in diameter, one hardly needs to be told that these flames are really gigantic. We shall see what they are presently. Regions of the Sun. The astronomer has divided the Sun into definite concentric regions or layers. These layers envelop the nucleus or central body of the Sun, somewhat as the atmosphere envelops our Earth. It is through these vapor layers that the bright, white body of the Sun is seen. Of the innermost region, the heart or nucleus of the Sun, we know almost nothing. The central body or nucleus is surrounded by a brilliantly luminous envelope or layer of vaporous matter, which is what we see when we look at the Sun, and which the astronomer calls the photosphere. Above, that is overlying, the photosphere there is a second layer of glowing gases, which is known as the reversing layer. This layer is cooler than the underlying photosphere. It forms a veil of smoke-like haze and is of from 500 to 1,000 miles in thickness. A third layer or envelope immediately lying over the last one is the region known as the chromosphere. The chromosphere extends from 5,000 to 10,000 miles in thickness, a sea of red, tumultuous, surging fire. Chief among the glowing gases is the vapor of hydrogen. The intense white heat of the photosphere beneath shines through this layer, overpowering its brilliant redness. From the uppermost portion of the chromosphere great fiery tongues of glowing hydrogen and calcium vapor shoot out for many thousands of miles, driven outward by some prodigious expulsive force. It is these red prominences which are such a notable feature in the picture of the eclipse of the Sun already referred to. During the solar eclipse of 1919, one of these red flames rose in less than 7 hours from a height of 130,000 miles to more than 500,000 miles above the Sun's surface. This immense column of red-hot gas, 4 or 5 times the thickness of the Earth, was soaring upward at the rate of 60,000 miles an hour. These flaming jets or prominences shooting out from the chromosphere are not to be seen every day by the naked eye. The dazzling light of the Sun obscures them, gigantic as they are. They can be observed, however, by the spectroscope any day, and they are visible to us for a very short time during an eclipse of the Sun. Some extraordinary outbursts have been witnessed. Thus the late Professor Young described one on September 7, 1871, when he had been examining a prominence by the spectroscope. It had remained unchanged since noon of the previous day. A long, low, quiet-looking cloud, not very dense or brilliant, or in any way remarkable except for its size. At 12:30 p.m. the professor left the spectroscope for a short time, and on returning half an hour later to his observations, he was astonished to find the gigantic Sun flame shattered to pieces. The solar atmosphere was filled with flying debris, and some of these portions reached a height of 100,000 miles above the solar surface. Moving with a velocity which, even at the distance of 93 million miles, was almost perceptible to the eye, these fragments doubled their height in 10 minutes. On January 30, 1885, another distinguished solar observer, the late Professor Tacchini of Rome, observed one of the greatest prominences ever seen by man. Its height was no less than 142,000 miles, 18 times the diameter of the Earth. Another mighty flame was so vast that, supposing the 8 large planets of the solar system ranged one on top of the other, their prominence would still tower above them. The fourth and uppermost layer or region is that of the corona, of immense extent and fading away into the surrounding sky. This we have already referred to. The diagram shows the dispositions of these various layers of the Sun. It is through these several transparent layers that we see the white light body of the Sun. The surface of the Sun. Here let us return to and see what more we know about the photosphere, the Sun's surface. It is from the photosphere that we have gained most of our knowledge of the composition of the Sun, which is believed not to be a solid body. Examination of the photosphere shows that the outer surface is never at rest. Small bright cloudlets come and go in rapid succession, giving the surface, through contrast in luminosity, a granular appearance. Of course, to be visible at all at 92,830,000 miles, the cloudlets cannot be small. They imply enormous activity in the photosphere. If we might speak picturesquely, the Sun's surface resembles a boiling ocean of white-hot metal vapors. We have today a wonderful instrument, which will be described later, which dilutes, as it were, the general glare of the Sun, and enables us to observe these fiery eruptions at any hour. The oceans of red-hot gas and white-hot metal vapor at the Sun's surface are constantly driven by great storms. Some unimaginable energy streams out from the body or muscles of the Sun and blows its outer layers into gigantic shreds, as it were. The actual temperature at the Sun's surface, or what appears to us to be the surface, the photosphere, is of course unknown, but careful calculation suggests that it is from 5,000 to 7,000 degrees centigrade. The interior is vastly hotter. We can form no conception of such temperatures as must exist there. Not even the most obdurate solid could resist such temperatures, but would be converted almost instantaneously into gas. But it would not be gas as we know gases on the Earth. The enormous pressures that exist on the Sun must convert even gases into thick, treacly fluids. We can only infer this state of matter. It is beyond our power to reproduce it. Sunspots. It is in the brilliant photosphere that the dark areas known as sunspots appear. Some of these dark spots, they are dark only by contrast with the photosphere surrounding them, are of enormous size, covering many thousands of square miles of surface. What they are we cannot positively say. They look like great cavities in the sun's surface. Some think they are giant whirlpools. Certainly they seem to be great whirling streams of glowing gases, with vapors above them, and immense upward and downward currents within them. Round the edges of the sun spots rise great tongues of flame. Perhaps the most popularly known fact about sunspots is that they are somehow connected with what we call magnetic storms on Earth. These magnetic storms manifest themselves in interruptions of our telegraphic and telephonic communications, in violent disturbances of the mariner's compass, and in exceptional auroral displays. The connection between the two sets of phenomena cannot be doubted, even although at times there may be a great spot on the sun without any corresponding magnetic storm effects on the Earth. A surprising fact about sunspots is that they show definite periodic variations in number. The best defined period is one of about 11 years. During this period the spots increase to a maximum in number and then diminish to a minimum, the variation being more or less regular. This can only mean one thing. To be periodic, the spots must have some deep-seated connection with the fundamental facts of the sun's structure and activities. Looked at from this point of view, their importance becomes great. The aurora borealis is one of the most beautiful spectacles in the sky. The colors and shape change every instant, sometimes a fan-like cluster of rays, at other times long golden draperies gliding one over the other. Blue, green, yellow, red, and white combine to give a glorious display of color. The theory of its origin is still in part obscure, but there can be no doubt that the aurora is related to the magnetic phenomena of the Earth, and therefore is connected with the electrical influence of the sun. It is from the study of sunspots that we have learned that the sun's surface does not appear to rotate all at the same speed. The equatorial regions are rotating quicker than regions farther north or south. A point 45 degrees from the equator seems to take about 2½ days longer to complete one rotation than a point on the equator. This, of course, confirms our belief that the sun cannot be a solid body. What is its composition? We know that there are present, in a gaseous state, such well-known elements as sodium, iron, copper, zinc, and magnesium. Indeed, we know that there is practically every element in the sun that we know to be in the earth. How do we know? It is from this photosphere, as has been said, that we have won most of our knowledge of the sun. The instrument used for this purpose is the spectroscope, and before proceeding to deal further with the sun and the source of its energy, it will be better to describe this instrument. A wonderful instrument and what it reveals. The spectroscope is an instrument for analyzing light. So important is it in the revelations it has given us that it will be best to describe it fully. Every substance to be examined must first be made to glow, made luminous, and as nearly everything in the heavens is luminous, the instrument has a great range in astronomy. And when we speak of analyzing light, we mean that the light may be broken up into waves of different lengths. What we call light is a series of minute waves in ether, and these waves are, measuring them from crest to crest, so to say, of various lengths. Each wavelength corresponds to a color of the rainbow. The shortest waves give us a sensation of violet color, and the largest waves cause a sensation of red. The rainbow, in fact, is a sort of natural spectrum. The meaning of the rainbow is that the moisture-laden air has sorted out these waves in the sun's light according to their length. Now, the simplest form of spectroscope is a glass prism, a triangular-shaped piece of glass. If white light, sunlight for example, passes through a glass prism, we see a series of rainbow-tinted colors. Anyone can notice this effect when sunlight is shining through any kind of cut glass, the stopper of a wine decanter, for instance. If, instead of catching with the eye the colored lights as they emerge from the glass prism, we allow them to fall on a screen, we shall find that they pass by continuous gradations from red at the one end of the screen through orange, yellow, green, blue, and indigo to violet at the other end. In other words, what we call white light is composed of rays of these several colors. They go to make up the effect which we call white. And now, just as water can be split up into its two elements, oxygen and hydrogen, so sunlight can be broken up into its primary colors, which are those we have just mentioned. This range of colors, produced by the spectroscope, we call the solar spectrum, and these are, from the spectroscopic point of view, primary colors. Each shade of color has its definite position in the spectrum. That is to say, the light of each shade of color, corresponding to its wavelength, is reflected through a certain fixed angle on passing through the glass prism. Every possible kind of light has its definite position, and is denoted by a number which gives the wavelength of the vibrations constituting that particular kind of light. Now, other kinds of light besides sunlight can be analyzed. Light from any substance which has been made incandescent may be observed with the spectroscope in the same way, and each element can be thus separated. It is found that each substance, in the same conditions of pressure, etc., gives a constant spectrum of its own. Each metal displays its own distinctive color. It is obvious, therefore, that the spectrum provides the means for identifying a particular substance. It was by this method that we discovered in the sun the presence of such well-known elements as sodium, iron, copper, zinc, and magnesium. Every chemical element known, then, has a distinctive spectrum of its own when it is raised to incandescence, and this distinctive spectrum is as reliable a means of identification for the element as a human face is for its owner. Whether it is a substance glowing in the laboratory or in a remote star makes no difference to the spectroscope. If the light of any substance reaches it, that substance will be recognized and identified by the characteristic set of waves. The spectrum of a glowing mass of gas will consist in a number of bright lines of various colors, and at various intervals, corresponding to each kind of gas, there will be a peculiar and distinctive arrangement of bright lines. But if the light from such a mass of glowing gas be made to pass through a cool mass of the same gas, it will be found that dark lines replace the bright lines in the spectrum. The reason for this being that the cool gas absorbs the ray of light emitted by the hot gas. Experiments of this kind enable us to reach the important general statement that every gas, when cold, absorbs the same rays of light which it emits when hot. Crossing the solar spectrum are hundreds and hundreds of dark lines. These could not at first be explained, because this fact of discriminative absorption was not known. We understand now. The sun's white light comes from the photosphere, but between us and the photosphere there is, as we have seen, another solar envelope of relatively cooler vapors, the reversing layer. Each constituent element in this outer envelope stops its own kind of light, that is, the kind of light made by incandescent atoms of the same element in the photosphere. The stoppages register themselves in the solar spectrum as dark lines placed exactly where the corresponding bright lines would have been. The explanation once attained, dark lines became as significant as bright lines. The secret of the sun's composition was out. We have found practically every element in the sun that we know to be in the earth. We have identified an element in the sun before we were able to isolate it on the earth. We have been able even to point to the coolest places on the sun, the centers of sunspots, where alone the temperature seems to have fallen sufficiently low to allow chemical compounds to form. It is thus we have been able to determine what the stars, comets, or nebulae are made of. A unique discovery. In 1868, Sir Norman Lockyer detected a light coming from the prominences of the sun which was not given by any substance known on earth, and attributed this to an unknown gas which he called helium, from the Greek helios, the sun. In 1895, Sir William Ramsay discovered in certain minerals the same gas, identified by the spectroscope. We can say, therefore, that this gas was discovered in the sun nearly 30 years before it was found on earth. This discovery of the long-lost air is as thrilling a chapter in the detective story of science as any in the sensational stories of the day, and makes us feel quite certain that our methods really tell us of what elements sun and stars are built up. The light from the corona of the sun, as we have mentioned, indicates a gas still unknown on Earth, which has been christened coronium, measuring the speed of light. But this is not all. Soon a new use was found for the spectroscope. We found that we could measure with it the most difficult of all speeds to measure, speed in the line of sight. Movement at right angles to the direction in which one is looking is, if there is sufficient of it, easy to detect, and if the distance of the moving body is known, easy to measure. But movement in the line of vision is both difficult to detect and difficult to measure. Yet, even at the enormous distances with which astronomers have to deal, the spectroscope can detect such movement and furnish data for its measurement. If a luminous body containing, say, sodium, is moving rapidly towards the spectroscope, it will be found that the sodium lines in the spectrum have moved slightly from their usual definite positions towards the violet end of the spectrum, the amount of the change of position increasing with the speed of the luminous body. If the body is moving away from the spectroscope, the shifting of the spectral lines will be in the opposite direction, towards the red end of the spectrum. In this way we have discovered and measured movements that otherwise would probably not have revealed themselves unmistakably to us for thousands of years. In the same way we have watched and measured the speed of tremendous movements on the sun, and so gained proof that the vast disturbances we should expect there actually do occur. Is the sun dying? Now let us return to our consideration of the sun. To us on the earth, the most patent and most astonishing fact about the sun is its tremendous energy. Heat and light in amazing quantities pour from it without ceasing. Where does this energy come from? Enormous jets of red glowing gases can be seen shooting outwards from the sun, like flames from a fire, for thousands of miles. Does this argue fire as we know fire on the earth? On this point the scientist is sure. The sun is not burning, and combustion is not the source of its heat. Combustion is a chemical reaction between atoms. The conditions that make it possible are known, and the results are predictable and measurable. But no chemical reaction of the nature of combustion as we know it will explain the sun's energy, nor indeed will any ordinary chemical reaction of any kind. If the sun were composed of combustible material throughout, and the conditions of combustion as we understand them were always present, the sun would burn itself out in some thousands of years, with marked changes in its light and heat production as the process advanced. There is no evidence of such changes. There is instead strong evidence that the sun has been emitting light and heat in prodigious quantities, not for thousands, but for millions of years. Every addition to our knowledge that throws light on the sun's age seems to make for increase rather than decrease of its years. This makes the wonder of its energy greater. And we cannot avoid the issue of the source of the energy by saying merely that the sun is gradually radiating away an energy that originated in some unknown manner, away back at the beginning of things. Reliable calculations show that the years required for the mere cooling of a globe like the sun could not possibly run to millions. In other words, the sun's energy must be subject to continuous and more or less steady renewal. However it may have acquired its enormous energy in the past, it must have some source of energy in the present. The best explanation that we have today of this continuous accretion of energy is that it is due to shrinkage of the sun's bulk under the force of gravity. Gravity is one of the most mysterious forces of nature, but it is an obvious fact that bodies behave as if they attracted one another, and Newton worked out the law of this attraction. We men say, without trying to go too deeply into things, that every particle of matter attracts every other throughout the universe. If the diameter of the sun were to shrink by 1 mile all round, this would mean that all the millions of tons in the outer 1 mile thickness would have a straight drop of 1 mile towards the center. And that is not all, because obviously the layers below this outer mile would also drop inwards, each to a less degree than the one above it. What a tremendous movement of matter, however slowly it might take place! And what a tremendous energy would be involved! Astronomers calculate that the above shrinkage of 1 mile all round would require 50 years for its completion, assuming, reasonably, that there is close and continuous relationship between loss of heat by radiation and shrinkage. Even if this were true, we need not feel over-anxious on this theory. Before the Sun became too cold to support life, many millions of years would be required. It was suggested at one time that falls of meteoric matter into the Sun would account for the Sun's heat. This position is hardly tenable now. The mere bulk of the meteoric matter required by the hypothesis, apart from other reasons, is against it. There is undoubtedly an enormous amount of meteoric matter moving about within the bounds of the solar system, but most of it seems to be following definite routes round the Sun like the planets. The stray erratic quantities destined to meet their doom by collision with the Sun can hardly be sufficient to account for the Sun's heat. Recent study of radioactive bodies has suggested another factor that may be working powerfully along with the force of gravitation to maintain the Sun's store of heat. In radioactive bodies, certain atoms seem to be undergoing disintegration. These atoms appear to be splitting up into very minute and primitive constituents. But since matter may be split up into such constituents, may it not be built up from them? The question is whether these radioactive elements are undergoing disintegration or formation in the Sun. If they are undergoing disintegration, and the Sun itself is undoubtedly radioactive, then we have another source of heat for the Sun that will last indefinitely. End of this part of Chapter 1.